All right, so welcome back to Math 383 Complex Analysis. So this is lecture 6. If you go online, the first 13 minutes from the version a couple of years ago is actually a review of path integrals, line integrals, and stuff like that. So if you want to see some of the stuff from multivariable calculus and just get some more intuition for how these calculations are done, that's a good introduction to just watch what's happening. Okay, so what I want to do today is I want to prove Cauchy's formula in some generality, and we can argue exactly just how general have we proved it, how rigorous do we need to be. See a little bit that holomorphic and analytic functions are the same, although we'll probably have to wait until the next lecture for that to be fully done, and then try to apply Cauchy's formula to do some integration. So what I might do is I might do some examples in a little bit less detail than is in the book or is in the previous years, just so I can mix up which examples we do so we see more possible integrations. You will notice that there will be a lot of pi's that come in when you integrate various quantities. And one of the reasons we have these pi's is these contours that we're doing in the 1 over 2 pi I that comes in complex analysis. There is a debate as to what is the right constant to study. Is it pi or 2 pi? Some people celebrate tau day, which is the 2 pi day. Some people actually like 4 pi, but there aren't that many of them. Why might you support 4 pi?
Are they physicists?
Yes, yes, they are physicists. You should have like a little bit more condensation in your physicists. So, if you look at some of the constants in electricity and magnetism, it's the 1 over 4 pi epsilon naught. It's coming from the surface area of the sphere. So 4 pi is a legitimate contender, but I think it's pi versus 2 pi, and complex analysis strongly makes the argument for either 2 pi or 2 pi I, but you're never going to get 2 pi I. When you do contour integrals, you often have a choice in what contour to do and what integrand to choose. At the end of the day, it doesn't really matter as long as you get the answer. Sometimes one path is easier to do than another. And so we'll try to talk a little bit about that. All right, so to try to minimize how often you have to read my messy handwriting, I thought I would just actually take some snapshots from the book and just try to review what we've done. And again, as I've said multiple times, I truly hate this part of the semester because I have to keep reminding myself, what do we know and what do we not know? So we started by proving Grocers Theorem, which says that if we have a triangle and a holomorphic function, and you're holomorphic on an open set that contains the triangle and the interior is also contained, then your integral is 0. So the real key that's going on in so much of this is that we contain the entire interior. This is why the donuts are going to cause trouble, because we don't include the entire interior. All right, so that was Grocers. The next was we then proved that if you are holomorphic in a disk, then you have a primitive. And in fact, we define the primitive by doing like a grid walk in Manhattan. We go east, west, and then we go north, south. And when we do that, there's this very specific path that we take. There's only one choice. Now, when we're on a circle, on a disk, this is not a problem. For more general sets, it becomes interesting as to when can you do something like this? If I have the entire interior contained, so a donut, an annular ring would not count. So then the book says, if we have a holomorphic function on an open set containing a circle C in its interior, then the integral of f over c is 0. And this is because we have the primitive, and we have this beautiful result that if you have a function that has a primitive, then its integral along a closed curve is 0. So long as it's holomorphic in the entire space, the boundary a little bit more maybe than the boundary, and definitely the interior. So the question is, why is the interior so important? So if I look at a donut or an annular ring, let's say I have something like this. So I don't have the region in the middle. If I want to try to get from one point to another, I could take a path like this, or I could take a rectangular path like this. And we would like to say that both of those paths will give the same answer. This now gives us a closed rectangular curve that goes around the annular ring, the center that we're missing. And if you think of the function 1 over z, we know that if we integrate the function 1 over z over a circle, it's not 0. So this tells us we have to be careful. What's going wrong? Well, we know that we can extend functions, so if I start off over here, I can draw these little disks and I can find my primitives in the disk. And we've talked about this, about what happens as you walk all the way around. And if we do it like this, there's the danger that maybe we don't come back to the same value when we started. And we see this when we think about the angle as we go all the way around. We start off with an angle of 0, but then as we go all the way around, it's coming back to 2 pi. And so we have some issues along that. If instead I give you something like this, we say I'm throwing away a small little part about a point that has an issue. If I start over here now and I start doing my circles and I start trying to go all the way around, I can't go all the way through. The fact that I've thrown this away. So the real question is, if I have 2 paths in my space, so here's my space, omega, here's one path, and here's another path. So let's call this gamma 1, let's call this gamma 2. Can I shrink from gamma 1 to gamma 2 and stay entirely in the space? Can we go from gamma 1 to gamma 2 entirely in omega? And do you see that the answer is definitely going to be no if we're missing the central region? So if we don't have the center, I can't deform my curve. So if gamma 2 is up there, there's no way, if you have it tied to these things, I can't just move it around. But if I had another path down here below, that I could move. And so it all comes down to, when can I move one path to another? So if I give you, a set like this, and here are 2 different curves, these 2 curves I could move from one to the other. And so, a little bit more explicitly, here's my set omega. Here's one curve. Here's another curve. And what I can do is I can draw a bunch of disks like this. And then on each of these disks, I can try to show that I can move from one to the other without any trouble. So if I just have part of a curve, I don't have a closed curve. So what would I want to do for these 2 curves? What would I want to add? So I want things that are going to cancel. So, I've got one curve here, say gamma 1, another curve here, gamma 2. And let's say I've got a couple of, transition points. And, here's one of my circles and everything is fine in here. So what might I want to add? Yes. Yeah. And so if I add these lines over here, and then I'll go through these lines in both directions. And if you look at this now, I'm going to have a bunch of closed curves. And if I go through gamma 2 in the opposite direction, so let's make this now a negative gamma 2, so it's moving like this, and a gamma 1 is moving like this, you can see we're going to have a lot of things canceling. Right? Because now if I look down here, I've got a closed curve. I'm in a nice disk. I have a primitive, so it's going to be 0. Yes. I want to basically just talk about just what the hell have we proven in terms of Cauchy's theorem. So, right now we've talked about it holds if we have a disk. What if we don't have a disk? If I have an oval, if I have a rectangle, is it still true? What if I have, the giant letter L? And so it's what spaces can I have a Cauchy's theorem? And essentially it's, I need to be able to have not just my 2 curves are in my space, but the interior of them is entirely in the space. The difficulty was the obstruction from when we're missing the center. So if it's not simply connected, and if I can't just go and pass, easily from one to the other. Yes.
So like if you chose specific paths and like a donut, it could work. But the problem
Yes.
is that it can't be every two paths.
Correct. So, that's why we said, down here, which almost looks like a smiley face. That smile would be fine because it stays away from the hole. Well, if it stays away from the hole, if you want, you could actually just, cut it out and make a space over there where everything is going to be fine. Yes.
Because you brought up like an oval or something like that, the same argument we did for like a certain like this would work for anything, but like homeomorphic with it, right? So like
Be very careful when you say homeomorphic. Let's say anything where I can always get from one point to another by going left, right, and then up, down.
okay,
Because it was extremely important in the argument that I specified the path I'm taking.
Yeah.
What you then want to do is you want to then say, as long as I have a rectilinear path, I want to be able to move from one rectilinear path to another. And so it really comes down to when can you deform from one path to another. And so over here, what we want to basically say is in each one of these little things out here, it's a closed curve. So it's going to be 0. All the red pieces are going to cancel. So that means the integral over gamma 1 is the same as the integral over gamma 2. Now, in each of these disks, we're going to have a primitive. It's not necessarily the same primitive as we move from one point to another. But how can primitives differ? Only by a constant. So when I look at the integrals over any of these red curves, even if I have a different primitive, since I'm integrating over a curve, it's the difference of the endpoints. And then the constant will change. So, each, closed curve gives 0. Okay, if primitives differ by a constant, as would cancel. And again, I'm not saying that they do differ by a constant. I'm just saying I don't even have to care. Yes.
we can put two disks here so that the points connected by the red line accumulate, so we can get any.
So that the points connected by the red lines
Accumulate, or can you, if you only need like two disks?
Yeah, I mean, I don't need any type of accumulation. I just need to be able to say, I have a disk where I have primitives. And so if the curves are too well separated, what might you have to do? Not more disks. If the two curves are very well separated, so maybe I have this curve, and maybe they're so far apart that it's hard to initially connect them. Add one what?
Add an extra curve.
Yes, we might have to actually add more curves. And so maybe we have a bunch of other curves and we slowly move. And then you keep pushing like that. So I'm just trying to give you a sketch of how you would make this a little bit more rigorous so that as long as you contain the interior, you're fine. Right now, what the book proved is it proved it in the special case when everything lived inside a disk. Not everything lives inside a disk. All of the stuff here is saying if it lives inside a disk. But when you look at regions like this, where you throw something away, we now have a nice region where no matter what curve I have, the interior is still contained in your set. And then everything is going to work. It's essentially just Green's theorem. And we've seen that Cauchy's theorem is essentially Green's theorem. So the book will talk about this in greater detail later in the semester. I wanted to just say a few words about this now to just see how would you extend what we're doing so that it doesn't have to just be on a disk. Why do we have to be careful about the interior? It's because of the function 1 over z. And if we try to integrate on the donut, we have a problem because we could go all the way around and we know that integral should not be 0. So there's got to be some obstruction. So it's nice to know, even if you can't figure out what the obstruction is, that there has to be some problem. I shouldn't be able to generalize this because I know the function 1 over z has trouble. And then trying to think, well, how is that causing trouble? And you can see, well, that when I go all the way around, I don't know that I return to the original value. So now the next thing is that if F is holomorphic on an open set that contains the closure of a disk, C is the boundary circle, then F of Z is 1 over 2 pi I, the integral of F of zeta, zeta minus Z d zeta, any point in the disk. So at this point in the semester, it's not even close, it's Cauchy over Riemann. Right? Riemann made a brief introduction with the Cauchy-Riemann equations, but Cauchy balanced them there. Okay, and what's the scoreboard?
20 to 10.
Wow, I'm surprised Riemann is doing that well. And of course, when I say I'm surprised that Riemann is doing that well, that doesn't count as 2 Riemanns, does it? It does count as 2 Riemanns, okay.
Or no.
I used to send my kids, funny things when they were at camp this summer, and one of them was, private sign, do not read. If you read the sign, you owe $500. You owe $500 for each additional sentence. And what? Even that sentence? Yes, even that sentence. Just like a running total. All right, so we'll have to then interpret as to exactly how many of those Riemanns are true Riemanns, as opposed to how many things are really Cauchy, because we want to be kosher for the Cauchy. Okay. So for Cauchy's theorem here, this is remarkable. Why is this remarkable? It tells you the value at any point in the interior is determined by integrating the function on the boundary. That means if you specify the value of your holomorphic function on the boundary, how much freedom do you have in the interior? None. The function is completely determined by its boundary values. You can think almost like differential equations or some physics systems like this, where you specify the boundary and the whole thing is now forced upon you. You may not be able to choose arbitrarily on the boundary. Not every choice on the boundary is going to give you a holomorphic function. But what this is telling you is, once you know the boundary, there's only one possibility for what the function is anywhere. Instead of doing this at the point Z, you could do it at the point 0 to just be a little bit nicer. Yes?
What is zeta here?
So zeta is a variable of integration. It's the point on the circle. So zeta is just ranging over the circle. So zeta lives on the circle. So it's just a variable of integration. So it's always important to remember, what are we integrating against? Okay. So essentially what we're doing here is we are looking at a function that's holomorphic in a nice region, and then saying the integral of a function that's holomorphic in a nice region has to be 0. What is our region? Well, our region is this strange keyhole where we throw away a small disk of arbitrarily small radius about Z, and then we have the two little things separated by a small amount. And so if we call this whole thing, and then the question is, what do we want to call everything? So we call C the outside. So I think we're calling gamma delta epsilon the whole thing. So here it's a circle of radius epsilon, and maybe here this is a width of delta. So the integral over gamma delta epsilon of f of zeta over zeta minus z d zeta equals 0. And that's because we're integrating a holomorphic function. Why is this holomorphic? So why is it holomorphic?
Holomorphic and theta times the non-zero.
Good. F is holomorphic, and 1 over zeta minus z is okay if zeta does not equal z. And because z is not in the interior, we're okay. And z is not in the interior. I'm sorry? Okay, z not in the interior or boundary. We just have to make sure zeta minus z is not 0. So zeta can never be equal to z. So we don't want zeta minus z to be 0. And the only way zeta minus z can be 0 is if zeta equals z. And since z is not in the interior of the boundary, zeta can never be z if we're inside this region. This is our region over here. So the function is going to be holomorphic. So what that means is that if we integrate over the circle, f of zeta over zeta minus z d zeta, and then we have to integrate over the small circle of radius epsilon, and I'm going to put a negative to say that we're integrating it in the opposite direction, what we want to do, of f of zeta over zeta minus z d zeta that equals 0. So I took the limit as delta went to 0. Now, I dealt with the fact that there's maybe a small little gap between those two cuts. Or if you wanted to, you could just have them already at the same, it doesn't really matter. So that if we bring it over to the other side, we then get the integral over c of f of zeta over zeta minus z d zeta is the integral over the circle of radius epsilon of f of zeta over zeta minus z d zeta. So all we have to do now is evaluate this integral. Now, zeta here is on a circle of radius epsilon. So circle of radius epsilon centered at z. So we can write zeta as z plus epsilon e to the I theta. Right? Because over here, zeta lives on a circle of radius epsilon. So we need to study the integral over c epsilon of f of zeta over zeta minus z d zeta. Zeta is equal to z plus epsilon e to the I theta, 0 less than equal to theta less than equal to 2 pi. Oh my God, it looks like we might actually be doing a real integral. An integral that we might remember how to do. What do you think f of zeta looks like on this circle? If you had to guess what f of zeta would be, what would you guess it equals? So, yeah, so I mean, so f of zeta is equal to f of z plus a correction. And then the question is, how much of a correction do we need? How careful? One of the things we could do is we could say, oh, we know the function is differentiable. So I could put it maybe in f prime, or I could just try to use continuity. Well, let's think. We have a 1 over zeta minus z. 1 over zeta minus z, is that large or small? Large, it's like 1 over epsilon. So this is huge. But we're integrating over a circle of radius epsilon. So we can bound it by the maximum value of the function times the length of the circle. What's the length of the circle? I'm sorry? 2 pi epsilon. So 2 pi epsilon times 1 over epsilon is of size 2 pi. So I don't actually need to have a great bound on the error term. I just need something going to 0. So this suggests I should not be using the fact that f is holomorphic in my expansion here. That's probably enough to just use f as continuous. And so we'll say plus maybe e of zeta z, where e of zeta z goes to 0 as epsilon goes to 0. We don't need a good estimate. And so what we would get is that it equals the integral of c epsilon over c epsilon f of zeta minus f of z plus f of z over zeta minus z d zeta. I've just done, one of the oldest tricks in the book, nothing, right? We can do nothing by adding 0. We can do nothing by multiplying by 1. The reason this is a good way to do it is now I have the integral over c epsilon of f of zeta minus f of z over zeta minus z d zeta plus f of z integral over c epsilon of d zeta over zeta minus z. Why did I pull the f of z out? Yeah, it's a constant. So now I have two integrals to do. The first one, I could actually say, well, because the function is holomorphic, this limit exists as epsilon goes to 0. And I could argue along those lines and say, because the function is differentiable, I know this quotient is bounded. Whatever it's bounded by, I then multiply by the length of the circle, so that tends to 0. The other possibility is to try to do some expression involving the error terms that I mentioned. You have multiple ways of proving these results. If you have an elephant gun and a fly is bothering you, is it okay to use the elephant gun? Yes. Now, there may be some collateral damage sometimes, but when you're trying to prove something mathematically, if you have some powerful machinery, is it okay to use it? Of course. Sometimes it's interesting to see what is the minimum theorem we need, what is the minimum result we need to prove something. This is especially important if you are using a recently proven result, which maybe is wrong. Maybe somebody used an incorrect argument and their estimate is wrong, and it actually doesn't work for up to 1/6, it only works up to 1/10. And so if you use the full strength of what was claimed, if that now turns out to be wrong, you then have to change everything. So sometimes it's interesting to just see what's the minimum amount you need to do. So you could try to see, is it enough to just use continuity? Or we can say here, as f is holomorphic, this quotient is bounded. So the integral in absolute value is thus equal to 2 pi epsilon times the bound, therefore it goes to 0. And for the other one, we're now just integrating, zeta is equal to z plus epsilon e to the I theta. So now, d zeta would be I epsilon, would be I epsilon e to the I theta d theta. And so this integral would just become f of z. The integral of theta goes from 0 to 2 pi. D zeta is I epsilon e to the I theta d theta. Zeta minus z is going to be epsilon e to the I theta d theta. Oh, well, that's not so bad. Everything cancels but the I, and we just get 2 pi I. Did I make a mistake? Oh, I have a d theta on the bottom. Thank you. And so now, removing the d theta that shouldn't be there, the epsilon e to the I theta is canceled. We look with integrating, just theta goes from 0 to 2 pi. This is an integral we can do. And we just get 2 pi I f of z. And so we now get that the integral, well, just moving these on, f of z is 1 over 2 pi I, the integral over the closed circle of c of f of zeta over zeta minus z d zeta. And that finishes the proof. Yes?
Reverse the orientation of the epsilon again?
Well, just remember that when we're walking through it, we're going clockwise. I'm sorry. We're going counterclockwise along the curve initially. Then we start coming down here. And as we go around the circle, notice we go around the circle clockwise. So when we are trying to write the curve, gamma of delta epsilon, gamma of delta epsilon has c in the counterclockwise way, and it has the c sub epsilon in the counterclockwise. And so we have to put in an extra minus sign to move it over. And yes,
We did this thing like before where we had this term of like the error correction thing.
mhm.
How do we know what that is? Like, I'm not really sure, like, I know.
Well, it's just, because the function is continuous, I can write it like that. And this has to go to 0 because the function is continuous, just the notion of being continuous function. But I know it's more than just continuous. I also know it's holomorphic. So I could do an f prime of zeta times zeta minus z plus an error term. I could do a more involved analysis. So the question is, what do you need to do for this problem? Is it enough to use just continuity, or do I need to use differentiability? And so I'll leave that as an exercise for you to see.
So we define like the gamma, like those extra pieces which aren't on the epsilon, we kind of just, we know that those are 0 because it's holomorphic and everything, right?
Yeah, you talking about the two lines?
Two lines, and also like the extra like little sliver of delta, sector delta, that wouldn't have.
Right. So I mean, basically, because everything is bounded in the limit as delta goes to 0, those two pieces are going to merge to each other.
Okay, but also, do they not, can't we just complete the contour?
You could also complete the contour, and then you would have a closed curve with the function. And so you could also do that by just finishing the whole circles. And that would also work, yes. There's lots of ways to get to the answer here in terms of how you want to do this. So well, countably many bad places would be bad because they would have to accumulate. And so let's just do finitely many bad places. So, again, we're doing things where there's only finitely many poles. And we'll see some, consequences later of what can happen if you have infinitely many bad places. Okay, so the next thing is, if f is holomorphic in an open set omega, then f has infinitely many complex derivatives. And moreover, we actually have an explicit formula. So this is a consequence of the fact that we just have f of z is 1 over 2 pi I, the integral over c of f of zeta over zeta minus z d zeta. So I know we have a couple of physicists here. How would a physicist prove this? Yes, and what are you doing as you wave your hands? What are you saying? Yes. Good. The derivative of the integral is the integral of the derivative. And I'm not going to fill in the box because it's a hand waving. Maybe I should draw like a hand instead of a box.
Do the hand.
Do the hand.
Or just like add fingers on the box.
Well, since we've been talking about the Simpsons, that would be my hand. All right. So this is the hand waving proof. Can you make this rigorous? Of course. There are resulted analyses that talk about when can you interchange the order of operation. I'm actually working on a book on when you can't interchange the order of operations. If anybody is interested in that, just trying to collect counterexamples, including a 1 or 2 line proof of the Riemann hypothesis, which we will see later this semester. If I could just do one illegal thing, I could prove the Riemann hypothesis in just 1 or 2 lines. This can be justified. In a lot of real analysis courses, they talk about, well, when can you switch orders of integration? And this is the Fubini-Tonelli theorem. If the integral of the absolute value is finite, you can switch. When can you switch the order of an integral and a derivative? There are conditions on something like that. If we don't have that, we have to be more careful. So the math proof is induction. And then if we want to look at the n plus first derivative at z, that'd be the limit as h goes to 0 of the nth derivative at z plus h minus the nth derivative at z over h. And when we look at that, it's going to be some integration. It's not going to be so bad. It's going to be n factorial over 2 pi I, the integral over c, and I'll have f of zeta over zeta minus z, oops, be very careful. Z plus H to the n plus 1 minus f of zeta over zeta minus z to the n. And this I can do. You know, I just have two different integrals, I can combine them. And now it just follows by doing algebra. You look at 1 over zeta minus z plus h to the n plus 1 minus 1 over zeta minus z to the n plus 1 is equal to, I'll let you fill that in or look at the book. And the algebra just comes from doing that. So when we subtract these, cross multiply, we have a difference of 2 nth powers. And you're going to get a zeta minus z. And the limit as h goes to 0, the two terms are going to coalesce into just a zeta minus z. Oh, yes, thank you. Yes. And in fact, there should also be a limit. So I need a limit as h goes to 0 of 1 over h. And d zeta. So now, yes,
Should the exponent in that same line?
I'll be n plus 1. Yep. Let's see. Trying to write things this way. So this would be zeta minus c to the n plus 1. And now it's just algebra, to go through and look at this. And the book goes through and does this in all the detail. All the ideas are gone at this point. You then just plug everything in and go forward. If you could just differentiate under the integral sign, it would be a lot easier. All right. So now, there are a lot of consequences. One of the consequences is, Cauchy's inequalities. So, again, Cauchy is, fighting over Riemann, although it's a little unfair, I think. So in the upper right corner in very small letters is just what we proved. The nth derivative was n factorial over 2 pi I, the integral over c, f of zeta over zeta minus z to the n plus 1. And so what we want to do is we want to just bound how large can the derivatives be at any point. And so this essentially follows by, if I have an integral, its value is going to be at most the largest value of the integrand times the length of the curve. What's the length of the curve? So integral in absolute value is less than equal to length of c times the supremum of the value of f on c. And then we have to multiply this by, no, we'll leave it like that. I'm just caring about the integral. And so what's the length of c? 2 pi r. And then the supremum we're just denoting by f of c. And so now when we put that in, we would get the nth derivative at any point z naught would be less than equal to n factorial over the absolute value of 2 pi I, and then the value of the integral would be 2 pi r, and then I have, remember down below, I have an r to the n plus 1, because I have a zeta minus z to the n plus 1. So when I put all the pieces together, we can see the 2 pi's cancel, and this will be n factorial, the large value of the function, divided by r to the n. So what's nice about this is it turns out that I have some control over how large the derivatives can be based on the largest value of the function on the boundary. Yes?
What is the R in this denominator?
Well, if you look, we have n factorial over 2 pi I.
Right, but where did that go on the right?
Well, the absolute value of I is just 1.
Oh.
Right? And so because the absolute value of I is 1, the absolute value of 2 pi I is 2 pi, which cancels with the 2 pi from the length of the circle. And so this tells you that if f is holomorphic, its derivative, its nth derivative can't be too large in terms of its values on the boundary. And so if its value is too large, then your assumption that it was holomorphic must be false. So we will see some interesting consequences of this later. Okay, what I want to do for the last bit of class is to talk about integrating some functions. So the first was a function I had when I was an undergraduate. F of x is sine squared x over x squared, and we want the integral from minus infinity to infinity of sine squared x over x squared. And you're supposed to use complex analysis to integrate this. But I noticed that if you're a little bit clever, if you let u, dv, du, and v be appropriate, so if we let u be sine squared x, du is 2 sine x cosine x dx, dv is x to the minus 2 dx, and negative x to the minus 1. So if we now integrate by parts, our integral is uv at minus infinity infinity minus the integral from minus infinity to infinity of v du. What's the boundary term going to be? It's going to be 0. And so when we plug everything in, this is going to just be the integral from minus infinity to infinity, the negatives reinforced, 2 sine x cosine x over x dx. But that's the same as the integral from minus infinity to infinity of the sine of 2x dx over x, which is the same as sine of 2x 2 dx over 2x. Right? And so if we change variables, this is the same as the integral from minus infinity to infinity of the sine of x over x dx. So if you remember your trig, you can actually reduce to doing it this way. Why is this valuable? It's a much easier integrand to work with. I don't have the squares of things. So when I was taking my journals at Princeton, I was actually asked that question. And I laughed because I had actually just reviewed it the night before. And I asked, this is supposed to be the complex analysis portion of the exam. Do I need to use complex analysis, or can I reduce it to sine of x over x and use real analytic techniques? So yeah, but however you want to do it is fine. And then they had some fun with me by giving me generalizations of the Fourier transform. So it was an interesting couple of minutes, but it was nice to have to be able to avoid these contours where maybe this part has to be in the upper part and this part has to be in the lower part. It's a little bit cleaner. Now just have sine of x over x. Now, if you want to prove that this converges, this is an alternating function. So, if you look at sine of x over periods of length pi, each one is going to contribute less than the one before. And so since you have an alternating series of decreasing absolute value, you know it converges. So we do know it converges. It's alternating and decreasing in absolute value. So we at least know that the integral makes sense. You do have to be careful about whether or not integrals exist. So for example, one of the most important ones is integrating from minus infinity to infinity of dx over 1 plus x squared. And I'll put in the 1 over pi. I'm only doing this because we're keeping track. This is actually the Cauchy distribution from probability. So it's arising in a completely non-complex way. And if we want to integrate this function, it turns out it's fine, and it turns out the value of this integral is 1. We'll see later how to prove this. Now, if you want to try to calculate the mean from probability, you would need, for mean, to do the integral from minus infinity to infinity of 1 over pi, 1 over pi x over 1 plus x squared dx. And the problem is the integrand x over 1 plus x squared is not going to 0. In fact, it's going to 0, but it's not going to 0 fast enough. If you look at this, what do you want to say this equals? What do you want to say this integral is? Yeah, why? Should be 0 as odd, right? However, what you really need to do is you need to look at the limit as a and b go to infinity of the integral from minus a to b of 1 over pi x over 1 plus x squared dx. That's what it means for the integral from minus infinity to exist. It shouldn't matter how I go to infinity. I should get the same answer. Case 1, if I take a equals b, I get 0. Case 2, if b equals 2a, we get the limit as a goes to infinity of the integral from a to 2a, because the integral from negative a to a just cancels, of 1 over pi x over 1 plus x squared dx. Well, that's approximately the limit as a goes to infinity. You can make this precise. 1 over pi integral from a to 2a. X over 1 plus x squared when x is really, really large is approximately 1 over x. So this is going to be the limit as a goes to infinity, 1 over pi. And then when the integral of 1 over x is log, the log of 2a minus the log of a is just the log of 2. And these are not the same. So unfortunately, this function is not integrable. It matters how you go to infinity. So even though it seems like it has mean 0, yes? Yep. Okay. The one with the sine squared or the sine of x with x? Okay. The arctangent? Yes. So if you remember, if I give you f of g of x equals x, these are inverse functions. F prime of g of x times g prime of x equals 1. This is the chain rule. So g prime of x is 1 over f prime of g of x. So if you know the derivative of a function, you can actually find the derivative of its inverse function. So if I want to find the derivative of arctangent, what is the tangent of arctangent of x? That equals x. So we get arctangent prime of x is 1 over tangent prime evaluated at arctangent of x. What is the derivative of tangent? Yes. I don't think so. I think it's close to that. I think it's positive secant squared. So the derivative of tangent is secant squared. So we have 1 over secant squared of arctangent of x. And in one of the worst bits of mathematical notation in the history of the subject, what function is 1 over secant? Cosine, right? Truly bothers me. So it's cosine squared of arctangent of x. So let's draw what's going on. I want an angle whose tangent is x. Well, here's my angle. Let's make that x. Let's make that 1. Right? That's the triangle that will have an angle whose tangent is x. What's the hypotenuse of this triangle? So the square root of 1 plus x squared. So that means that the cosine of theta is the cosine of arctangent of x is 1 over the square root of 1 plus x squared. So that means cosine squared of arctangent of x is 1 over 1 plus x squared. And so now, so if I want to now integrate from, let's go from 0 to infinity of dx over 1 plus x squared. This is the integral from 0 to infinity of arctangent prime of x dx. All right. Anybody want to tell me what is the integral of arctangent prime? Arctangent. So we get arctangent of infinity minus arctangent of 0. What angle has a tangent of 0? 0. What angle has a tangent of infinity? Pi over 2. And we're only going from 0 to infinity, that's why you have to double it. So we can actually solve 1 over 1 plus x squared. When you look at this, it should be a little surprising that pi comes into play, but maybe if you think of some of your trig identities. What we'll see next time is, what if I give you the integral from 0 to infinity of dx over 1 plus x to the n? You know, can we answer something like that? And we'll see how complex analysis helps us to do stuff like that. All right, so this is a good place to stop.